Thank Okay, hello everyone. Today we talk a little bit more about curves on the surface and certain special curves. And these curves were called geodesics, and the properties that you will have will be analogous to these properties that you know from a plane curve, like a curve in a plane that is straight. And that we discussed last time has like certain properties, like for example that the acceleration is zero, which is equivalent to having parallel tangent vectors for all times, and that it's the shortest connection between its endpoints. So these things you know all very well for curves in like a plane. And the question is now, what is like if you consider a very complicated surface, and you look at like certain curves on that surface, and you would like to know what are like the analog of straight lines, and can you characterize them maybe in like many different ways. And today we will focus mostly on the first three properties. So what is like the straight line, and how you can relate it to the acceleration and to the tangent vectors being parallel. So that will be the topic for today, and then next week we will focus more on the shortest connection property. So that's the plan. So let's directly dive in. So we have like C like a constant speed curve. In the surface of constant speed v, which we call that this is just meaning that the absolute value or the norm of the tangent vector is constant. And consider a frame on S, which is adapted, so E1, E2, E3, adapted frame. And it's natural that once you have a frame, you have essentially E3 is like fixed once you say that it's adapted because it has the norm. So now you have E1 and E2 you can like choose freely. But we also have a curve on S. So it would be natural to say like, okay, at least one of them, say like the first one should be connected to the tangent vector of our constant speed curve. So satisfying the property that E1 at the point C of t is some multiple, the scaled version of speed, of the velocity. So picture is you have a curve in S, and then you have E1, and E1 has to coincide along the curve with the tangent vector, but apart from that, you can freely choose whatever you want. But it's nicely smooth, and if you restrict it to a curve, it's exactly the tangent vector. So that's E1. E2 is some vector that is orthogonal to that, and E3 is pointing out of the blackboard. So that's the setting, and what we would like to analyze is essentially the second derivative, the acceleration, because that was the second point. Like like these straight lines are like certain curves that have like a nice acceleration. So let's try to see what happens to the acceleration on a surface, and see maybe we can connect that. So we already know, because it has constant speed, that that the inner product of the acceleration with the velocity will be 0. So that can tell you, tells you that like the second acceleration doesn't have any component in the c direction. Or since like c dot is proportional to E1, means that the second the second derivative, the acceleration, doesn't have any component that points in the E1 direction. It only has something that points in the E2 direction and something in the E3 direction. So that means there exists functions, and they are called k, g of t, and kn of t, such that the second acceleration of t, by a convention it's scaled with v squared here, equals to k of t, which is the factor in front of E2 of c of t, and then a second factor, which is the kn of t, which is the component in front of the free component. So that just follows that there are like these kind of functions, just follows from this fact that there's no E1 component, and then there is something in front of E2 and something in front of E3, and we give these somethings a name which is kg and kn, and they have like then using that we can write actually the curvature. That's why we called it k and like scale it like that. Namely, we the curvature of the curve is given as the norm of the second acceleration over v squared by definition, and since E2 and E3 are unit speed unit vectors that are orthogonal, you see from that formula that it's just the square of kg of t, so you do it at every point t, plus kn squared of t, and then we take the square root of that. So that's why these functions are called k and then some subscript. And the subscript is coming from the name that these ones will be called the geodesic curvature, and this one will be the normal curvature. Why that's called normal curvature makes sense, because it's essentially the factor in front of the normal. But why that one will be called a geodesic one, that will be discussed later. So that's the curvature of the curve, if you just think of that as like a normal curve in C. So we need also some expression of these kg and kn in terms of the connection forms. And from this, we recognize that the second derivative scaled with the factor of v, this one is nothing else than taking d dt by definition of c dot of t over v, and c dot over v, that's the expression that we had. So this one is just E1 at the curve. So this one would be d dt of E1 in c of t. So that's the reason why we put the v also here. So now we use the just a definition of the tangent map, or like chain rule, depending on how you view it, to write this as t of c of t of E1 in the direction where we have ddt inside, so that gives us just c dot of t. And this expression we have seen now quite a lot of times. This one we can write as, in terms of the connection forms, as omega 1, 2, c of t E2, c of t plus omega 1, 3, c dot of t E3 of c of t. So that's nice, because now we get like a formula that looks very much similar to this formula here, except that there's like a scaling of v wrong. Otherwise, we can read off what these k, g, and kn are in terms of these connection factors here. What we read off is the following, namely that kg equals to omega 1, 2, and then of c dot of t over v, and kn of t equals to omega of 1, 3 of the same expression. So that's the two formulas that we get now. And as I said already, so this one is called the geodesic curvature of C as a curve inside of S. And from this formula, because it's the 1-2 component evaluated at C dot, it measures how fast the tangent vector C dot is rotating towards E2. And this formula, that's why I wanted to write it like that, only depends on omega 1, 2. It only depends on omega 1, 2. And we have seen last time in quite some length that omega 1, 2 is the intrinsic part of the connection. So, because this one, the geodesic curvature also only depends on omega 1, 2, okay, it is intrinsic. So, you can think of that. It's like a really good way of thinking of this is like, what is the curvature of the curve for someone that lives inside of the surface? So that's the intrinsic curvature. If you're just like a small inhabitant, like an ant living on the surface, and someone draws you a line there, you say like, okay, what is like, how can I measure the curvature of that thing? The only things that you can measure are E1 and E2. You can like track how C is changing with respect to E1 and E2. And what you then get is essentially that's like the curvature that you can recognize. So you can like recognize if like, if I draw here a line, I can recognize by just looking at that if that makes like a curve or not. But I don't know, like there is no version of like that I know from the outside, like how maybe some aliens see this curve that I draw here, and they recognize maybe that the Earth in itself is curved, and that's why the curve has some additional curvature. And that's the part that is coming from the Kn of t. And it's this part here is called the normal curvature. Normal curvature of C, the curve. So it's not like the normal curvature of the surface, but it will be very much related to that. We will see that in a second. And by just looking at that formula with the interpretation that we had for the connection form, it measures how fast C dot, the tangent vector, is rotating towards the third vector, which is the normal. So that's the interpretation. Clearly, it depends on omega 1 free. So it's extrinsic. And it's more like the curvature seen from outside of C is seen from outside the surface. So it's like these two functions that we are a priori only defined by this formula as like the components that are in an E2 direction and E3 direction of the acceleration. They have like this nice interpretation once you can rewrite them as like in terms of the connection forms. And it allows us to now put like a definition which is very much similar to this definition over there, because we now have like the tools to make that analogous. So the definition is the following. The curve C with constant speed in S is called a geodesic. Any of the following equivalent properties hold. So we would like to say things that are like similar to being a straight line, but now a straight line for essentially from the end view. So like, of course, it doesn't make much sense to say like that it's really literally a straight line. If I have like the sphere, I can't say yeah, I don't want to generalize the notion of like that it means to be just like a straight line, but I want like to have the property as like seen from the surface of the Earth, what would be the analog of a straight line. And people can just measure, as we just discussed, we can only measure these geodesic curvatures, like the curvature that the curve intrinsically has when measured on S. So the analog of the being a straight line would be that the Gaussian curvature of the curve for all t's is 0. So that you can think of as intrinsically straight. So it's straight as measured from inside. So you for an ant going on the surface, it can't recognize at all that the curve has some curvature in there. So that's the first property that would be analog to the straight line property. The next one, what is the analog of that the curvature is 0, that the acceleration is 0. So that no longer holds true if you just have like this property that the k of t has to vanish. We can we don't know anything about this kn of t. That can be arbitrary. It just says like, what we only say is that this expression here has to be 0. We don't say anything about the kn of t. So in this case, the curvature of t can be non-zero, but it has to be only in a normal direction. Yes. Completely in the normal direction. So it's proportional to the normal, and then like up to some scaling with the speed, it's like actually the scaling factor is then the normal curvature. So that's this property. The third property essentially comes from this fact, is that if you know that k of t is 0, then we also know that this expression has to be 0. So that means that omega of 1, 2 of c of t equals to 0. And we will, essentially that will be like today's job, to discuss how is that relation, that it's like a relatively ugly equation on c of t. Why would you call that parallel? So that will be for today job to discuss what is the relationship of that equation with the notion of being that these vectors c of t being parallel. And then next time we will see that we can also add a property here, shortest length property. So that will be next class. So that's like essentially the 4 same properties that we know from the plane curves, but now for like a curve in the surface. Okay. So let's see some examples. The first one would be not to verify that it's not just analogous, but like really boils down to the properties that you know if you have a curve that is in the plane. So that's the first example. When we assume that S is a plane, is just a plane, like say in R2, then you have a curve, say R2 as xy, plane in R3. Then C of t we can think of as a function from the interval into R2, and then C of double t will be some vector, but it will be again in R2, but because the curve is like there. So that being is normal, which in this case just like the z-axis, if and only if C of t actually is 0, because there will never be like a normal direction, because it's just like a curve that like moves here. If you take the second derivative of that curve, it will still be a vector in R2, and that vector will be never pointing in a normal direction because it will always be contained in the plane. So if you take, if you say that it has to be normal, then it actually means that it has to be 0. So that means this property that we had here, that like the geodesic property, the second one, is actually equivalent to the first one. That it's so upshot is that geodesics in R2 are just straight lines. Okay, so that's a bit of a boring example. So what are the geodesics on the sphere? Does someone has an idea of what geodesics are on the sphere? Yes. So these are the great circles. So a great circle is circle is the intersection of the sphere with a plane through the origin. So you take your sheet of paper, which you can orient as you want, and you have your sphere, and you just cut essentially once through the sphere, then you get like one circle that will be like cut out by, if you take like the intersection, and these ones are called great circles. So we just take a plane for the origin. How do I want to do that? and then we get here the circle that is cut out by this plane. So you have a plane through the origin, and then you just intersect them. And that gives you a curve. And these curves are called great circles. If we parameterize such a great circle, to have constant speed, then it is a geodesic. And the reason is that, like, if you look at such a curve, you see that, like, it always the acceleration will be such that it's like points directly to the origin. Fully pointing to the center of the sphere. And that means that the acceleration is like pointing to the center, and the center, the vector that points from the origin to point, that's just like the normal vector at that point. So that means we see for this second property that it's completely in a normal direction. Corresponds to the normal. And then it's a geodesic because of the second point. Okay, so that gives you some idea of how like these geodesics look like on the sphere, at least, or some geodesics. Okay, so we would like now to discuss a little bit more about this property here, which I said like means that these vectors t dot of t are parallel. So that I did by analog here because that was the third property. So we would wish that this property here is something like a parallel. So we need to discuss a little bit how it looks like, what it means for vectors being parallel. So in the plane, geodesics are exactly those curves with parallel tangent vectors. But that's clearly not like the case, at least not naively, if you look, for example, on the sphere. Like these ones were the great curves, but like what is the tangent vector of a great circle doing is like it starts maybe up here and then it just like rotates around once I go. Like it's a big circle, so the tangent vector will be like it's hard to show that, but like if you have like the sphere and then you take a great circle, what the tangent vector will be doing is to point like outwards and then it slowly rotates and then goes back. So these vectors are like barely you would call them parallel, right? Like they start out like this and then rotate slowly around. They are definitely not what you would call parallel in an E sense, where we just have like vectors which are like these vectors I call normally parallel, and not like this vector that points outwards here and then rotates there and then points to the back. So these vectors are, so we have to discuss a little bit what it means for vectors to be a parallel on a surface. The question is, what is the notion of parallel on a surface? So first of all, we have to talk about what it actually means to have vectors that are like somehow defined along a curve. So we would like to compare the tangent vectors with each other. So we have a curve, and we have essentially a vector field along the curve. So at every point, we get a certain vector. So here at that point, which is C of t, we have a certain vector which we call x of t. And then we would like to say, at the data point, we would say what it means for these vectors to be parallel. But first, to define what that means, we need the following definition. So that C has be a curve, like a nice smooth curve, and then a vector field along C is a smooth map which is usually denoted by x, also from the same interval into vectors, and we would like to have that at every point x of t at every point, every time instance t, we would like that vector to be a tangent vector, as in this picture, a tangent vector at C of t. So, property. So it should be tangent to S, not something in a normal, and it should be also sitting at the right point as the base point for all. So the example here that is also the most interesting one for us is C of t where we just take the first derivative of C. That gives us a vector, and because the curve was restricted to be in S, means that the tangent, like the derivative, is a tangent vector, and that one has to be a tangent to S. So this one is a vector field along the curve C itself. And now the important observation is that the derivative of x, that will be is a map. We just take the derivative in respect to t of x. That's again a map from some times instances to R3, so that's a vector. But this vector here is usually not tangent again. But ddt of x of t is usually not tangent to the surface. So for example, what we already saw before, if x equals to the tangent vector, then ddt of x is nothing else than the second velocity. And we have just discussed that the second, the acceleration of the curve has some components in E1 and E2 direction, but also some components in n direction. So the main idea now is to start with such an x, take its derivative that gives us like a form that has like a vector, and then we decompose that vector into something that is tangent to s and something that is not tangent to s. So it's something that is normal. So that's the idea. And it's handy to do that actually with respect to a frame again. So for this purpose, choose an adapted frame E1, E2, and E3 on S. And we don't require any connection between E1 and the tangent vector. So, not necessary E1 parallel to C dot. Then we can write x of t as a linear combination of E1 and E2, because E1 and E2 are spanning the tangent vector. So what we have here is we have F1 of t, E1, C of t, plus F2, E2 C of t for some smooth functions f1, f2. So these are the coefficients of x of t in E1 direction and in E2 two direction. So now let's take us the derivative that we would like to study. So d dt of x of t with respect to this formula. So d dt x of t equals to, and then we get like two contributions from each of these terms. The first one will be the derivative of in f, and then the second one will be the derivative in the direction of the E1s and E2. So f1 of t, E1 of c of t plus f1 of t times the derivative of this guy in t direction, and then we can write this one as the tangent map. And similarly, plus the same expressions. Just so now recall that we can write this guy here again using the connections. So we can write this one as omega 1, 2 c of t in E1 direction, c of t plus omega 1, 3 ct E3 c of t. We do that because then what we see is that we get certain contributions in E1 direction, so that will be this term plus this term. Then we get certain contributions in E2 direction, and from these terms over here we get also certain contributions in E3 direction. So let's collect all of them like by the direction. So what we end up in total is that we have f1 dot of t plus omega 1, 2 and c of t. So that's the times f1. Oh, sorry. So that's the E2 direction. We get something from this term here that is coming from in the f1 direction. So that's f2 comes from here times omega 2, 1 c of t. And then E1 of c of t.